All right, today we're going on an incredible journey, but not to the stars. Nope, we're going thousands of miles straight down, beneath our own feet. We're about to explore a hidden world of just unimaginable pressure and heat. A world we could never, ever visit, but one we're starting to understand with, honestly, stunning clarity.
And that really is the central question, isn't it? It's this wild paradox. We have telescopes that can peer into galaxies billions of light years away, but the world right under us, it's almost completely invisible. So, how have we managed to piece together this unbelievably intricate puzzle of our planet's interior without ever once laying eyes on it?
So here's our game plan, our roadmap for this amazing descent. We're going to start with the sheer scale of the challenge. Then we'll learn how we literally listen to the planet's heartbeat. After that, we'll journey through the layers, solve a seismic mystery, uncover some truly bizarre structures at the core's edge, and finally, we'll see how this hidden world protects every single one of us on the surface.
Okay, first things first. Let's just try to wrap our heads around the scale of this journey. We're talking about a distance of roughly 4,000 miles to get to the center of the Earth. And when it comes to trying to explore that directly, well, let's just say we've barely scratched the surface.
Just look at that number, 0.2%. That says it all, really. The deepest hole humanity has ever managed to drill, the Kola Super Deep borehole, only got about 7.5 miles down. That is just 0.2% of the way to the center. It's like trying to understand an entire person by just looking at a single strand of their hair. It's impossible. And that is exactly why we've had to get so clever.
So if we can't drill there, how in the world do we see inside the Earth? Well, the answer is, we listen. We listen to the incredible energy released by earthquakes. These things, called seismic waves, act like a planetary-scale ultrasound, sending these powerful vibrations crisscrossing through the entire Earth, and they carry clues about everything they pass through.
Now this is where it gets really interesting, because there are two main types of these waves. P waves, or primary waves, are compressional. They push and pull, kind of like a sound wave, and they can travel through just about anything, solid or liquid. But then you have S waves, or shear waves. They move side to side, like shaking a rope. And here's the kicker. That kind of shearing motion is physically impossible in a liquid. And that one simple fact, well, it became the master key to unlocking the deep Earth.
And this is the discovery that changed everything. Scientists started noticing that after a big earthquake, their seismographs on the other side of the planet would pick up the P waves just fine. But the S waves, they were just gone, vanished. There was this huge shadow zone where they never appeared. And there was only one possible explanation. Deep inside the planet, those S waves must have slammed into a massive liquid barrier that they just couldn't get through. This was it. The first solid proof that Earth has a huge liquid outer core.
All right, so now that we have our seismic toolkit, let's actually start our journey down. We're going to peel back the layers of the Earth one by one. It's kind of like opening up a set of those giant planetary nesting dolls.
We start right here, on familiar ground, the crust. And, compared to the rest of the planet, it is shockingly thin. Seriously, it's like the shell of an egg. This is the fragile layer we all live on, broken up into those tectonic plates whose slow, grinding dance shapes all of our continents and oceans.
Okay, go deeper. And you hit the mantle, the thickest layer of our planet by far. Now, even though it's solid rock, the heat and pressure down there are so intense that it actually flows over millions of years. Think of it like super, super thick caramel. This slow, churning motion is the powerful hidden engine that drives the tectonic plates up on the surface, causing earthquakes and building entire mountain ranges.
And just to help you wrap your head around its insane scale, think about this. The mantle makes up a whopping 84% of our planet's total volume. 84%. We're basically living on a tiny, fragile little rock raft that's floating on top of this immense, slow-motion ocean of solid rock.
And now we arrive at the layer we first discovered with that S-wave shadow zone, the outer core. This is a churning, swirling ocean of molten iron and nickel, unbelievably hot and in constant, violent motion. And as we're about to see, the churning of this metallic sea is responsible for something that is absolutely critical to our survival up here.
For a long time, discovering the liquid outer core seemed like the end of the story. People thought, great, we figured it out. But then, one brilliant seismologist started noticing some clues in the data that just didn't add up. And that kicked off one of the greatest scientific detective stories ever.
Her name was Inge Lemon. She was a Danish seismologist, and back in 1936, she was studying the seismic waves from a major earthquake in New Zealand. And she saw something, weird. Some seismographs way over in Europe were picking up these faint P waves in places where they absolutely positively should not have been. It was a complete puzzle that defied the model of the Earth everyone was using at the time.
And this is where her genius really shines. She just walked right through the logic. Okay, step 1, the earthquake sends waves out. Step 2, the expected waves arrive where they should. But then step 3, these weird faint echoes also show up in the shadow zone. What could cause that? Lehman's revolutionary idea, step 4, was that these are P waves that had traveled all the way through the liquid outer core and then bounced off of a solid object right at the very center, deflecting them to these unexpected spots. Just like that, she had discovered the inner core.
And what a bizarre place it is. The inner core is a solid ball of metal, mostly iron and nickel. Now get this, the temperature there is as hot as the surface of the sun. We're talking thousands of degrees. So why is it solid? The answer is one word: pressure. The crushing weight of the entire planet is pushing down on the core, squeezing those atoms so incredibly tight that they are physically locked into a solid state, even at those insane temperatures.
So you might be thinking, okay, inner core, outer core. Our map's complete. But nope, not even close. As our seismic tools get more and more sensitive, they are revealing that the deep Earth is way, way stranger than we ever imagined. The journey of exploration, it's really just getting started.
You gotta hear this. Using a technique that's basically a CT scan of the entire planet, scientists have found colossal structures sitting at the base of the mantle, right on the boundary with the core. And when I say colossal, I mean they've found mysterious formations that can be over 100 times taller than Mount Everest. The landscape of the deep Earth is more dramatic than anything we have on the surface.
So what are these things? Well, the biggest are 2 continent-sized blobs called LLVPs. Seismic waves slow way down inside them, which hints that they might be chemically different from the rest of the mantle, maybe even leftovers from Earth's formation. Then you've got these ULVZs, pockets that might be partially molten rock. And my personal favorite, slab graveyards. These are literally the final resting places of ancient tectonic plates that sank down into the mantle hundreds of millions of years ago. A fossil record of our planet's past, buried thousands of miles deep.
Now look, seismic waves are an incredible tool, but at the end of the day, it's all indirect evidence. To really truly understand what's going on down there, scientists have to find a way to test it. And to do that, they somehow have to replicate the absolutely insane conditions of the Earth's interior right here in a lab.
And this is how they do it. It's called a diamond anvil cell. They use the hardest substance we know of, diamonds, to squeeze a teeny tiny sample of rock or metal with pressures millions of times greater than our atmosphere. Then they can blast it with lasers to heat it up to thousands of degrees. This lets them watch firsthand how these materials behave at the core mantle boundary or even inside the inner core itself. It's how they prove the theories that come from all that seismic data.
So, after this whole incredible journey, we have to ask the big question. Why does any of this matter? It's fascinating, for sure, but does it affect us? Well, it turns out that this hidden world beneath our feet is the entire reason our planet is a vibrant, living world and not a barren, dead rock like Mars.
The secret is something called the geodynamo. As our planet spins on its axis, it causes all that liquid iron in the outer core to churn and swirl in these massive, complex patterns. And because liquid iron is a great electrical conductor, all that motion generates powerful electrical currents. Those currents, in turn, create a massive magnetic field that wraps around our entire planet like a protective shield.
And here's the thing. Both parts of the core are absolutely essential. The liquid outer core is the engine. Its churning motion generates the field. But that solid inner core, it plays a crucial stabilizing role. It acts like an anchor, organizing the chaotic mess in the outer core and helping to maintain a stable, powerful magnetic shield. And without that shield, the solar wind from the sun would have stripped away our atmosphere and boiled off our oceans eons ago.
And that brings us to one last, kind of mind-bending thought. Our planet is slowly, very slowly, cooling from the inside out. As it cools, the solid inner core is actually growing by about 1 millimeter every year as more liquid iron from the outer core freezes onto its surface. But that process can't go on forever. So, what happens to our planet, to all life, to everything when our dynamic liquid core, the engine of our protective shield, finally cools and freezes solid billions of years from now? It's a pretty humbling reminder that even our planet has a life cycle, driven by the immense, powerful, and hidden world at its very center.